In today's video, we'll explore how a neural network can help a robot arm sort objects based on color and size. We'll break down how this network works, step by step, to see how it turns data into decisions. Imagine you're programming a robot arm to pick and sort objects by their color and size, like red, blue, or green, and small, medium, or large. To make this possible, we need to teach the robot how to recognize these features and make decisions based on them. That's where a neural network comes in. Let's start with the inputs. Our neural network receives data about each object, specifically its color and size. For instance, if the object is red and small, these details are fed into the network as inputs. These inputs are connected to neurons through weights, which determine the importance of each feature in making the sorting decision. The network learns these weights during training, adjusting them to improve its accuracy. Inside the network, each neuron sums up the weighted inputs. This is a crucial step where the network combines color and size information to form a clearer picture of the object. For example, if the network has learned that color is more important for sorting, the weight for color might be higher. This means the final sum leans more heavily on the object's color when making a decision. Once the network calculates these sums, the next step is to pass them through an activation function. For our sorting task, we'll use the Softmax function. The Softmax function converts the summed values into probabilities that add up to 1. These probabilities indicate how likely it is that an object belongs to a specific category, like red and small, blue and medium, or green and large. This way, the neural network helps the robot arm make smart, data-driven decisions, ensuring each object ends up in the right place. And there you have it. That's how a neural network can be used to help a robot arm sort objects by color and size. It's all about turning data into decisions, one step at a time. The Softmax function, denoted by sigma, takes a vector of values, often the output of a neural network, and converts them into probabilities. These probabilities always add up to 1. For this example, imagine we have 3 categories with corresponding scores of 0, 1.0, and 0.1. These scores could represent anything. Say how strongly the network believes an image is a cat, dog, or a bird. We then apply the Softmax function. For the first value, 2.0, the function calculates the exponential of 2.0, divides it by the sum of the exponentials of all 3 values, and arrives at a probability of 0.71. This process repeats for the other 2 values, giving us 0.26 and 0.03. Now let's visualize these probabilities on a bar graph. Here, you can see how the Softmax function has transformed the raw scores into probabilities that clearly show the most likely category. The first category, with a probability of 0.71, is the most likely, followed by the second and third categories.